Welcome to another deep dive. Today, we're getting straight to what really matters on a topic that's, well, truly shaping the landscape of computer science and software engineering. We're talking about the Rust programming language. We've pulled together a whole stack of sources here to really unpack what Rust is, where it came from, and, why it's become such a significant player. Our mission, to basically extract the most crucial takeaways so you can quickly grasp the essence of Rust without feeling overwhelmed.
That's right. Yeah, if you're looking for a concise but still thorough introduction to Rust, well, this deep dive is definitely for you. We'll explore its unique design philosophies, its key features, and why it's gaining so much traction in all sorts of software projects. From high-performance web services all the way to fundamental OS components.
Okay, let's unpack this then. At its absolute core, what is Rust? What makes it different?
So Rust is a general-purpose programming language, but its main emphasis really is on performance, type safety, and concurrency. What's truly fascinating, I think, is how it manages memory safety without needing a typical garbage collector.
Right.
Instead, it uses this thing called the borrow checker, and that helps prevent memory safety errors, data races too, right at compile time.
Okay, so no garbage collector, but it's still memory safe. That sounds like a really powerful combo for developers.
It is.
How did this whole approach come about, this innovative idea?
Well, it actually started, way back in 2006. It was a personal project by Graydon Hoare. He was working at Mozilla Research at the time. And the story behind it is kind of relatable, actually. He apparently started because he was frustrated with a broken elevator in his apartment building.
Huh, no way. A real-world problem sparking innovation. I like that.
Exactly. And he even named it after a group of fungi, rust fungi, because they're known for being, quote, over-engineered for survival. It's kind of a nod to its robust design goals.
That really humanizes it. Okay, so personal project first, but then Mozilla got involved officially.
Yes, yeah. Mozilla officially sponsored the project in 2009. People like Brendan Eich, executives there, they were really intrigued by the potential, using Rust for a safer web browser engine. And Hoare himself, he really stressed prioritizing good ideas from old languages, not just inventing new stuff. He called Rust technology from the past come to save the future from itself.
Interesting.
So that means it pulls inspiration from concepts in languages like CLU, Erlang, even OCaml. In fact, its early compiler was actually written in OCaml.
Got it. So it's built on these time-tested concepts, but definitely with a modern focus on safety and performance. Okay, let's dive into some of those core features then, the things that really define Rust. Its syntax, for example, looks somewhat familiar, doesn't it?
It does, yeah. Rust's syntax has similarities to C and C++A, which, can make it a bit more approachable if you're coming from that background. But it's also really heavily influenced by functional programming languages, like OCaml, as I mentioned. It was, in fact, kind of specifically targeted at, let's say, frustrated C++ developers who were looking for better safety, more control over memory layout, and solid concurrency.
You mentioned memory safety without a garbage collector. How does Rust actually pull that off? This seems to be the big thing people talk about.
Yeah, that's a crucial question.
Yeah.
And it brings us to Rust's ownership system. It's really core. Basically, at compile time, every single value in Rust has to have one variable that's called its owner. Now, when you assign values or pass them to functions, they get moved between owners. That means the original variable can't be used anymore.
Okay.
But, and this is, critical values can also be borrowed. You use references for that. So they're temporarily passed, ownership doesn't change, and then they're returned to the owner.
So if a function takes ownership, the original variable's gone, essentially. But if it's just borrowed, you can still use it afterwards.
Exactly right. And this really strict set of rules, which the borrow checker enforces, prevents all those common nasty errors like dangling pointers. Where you're trying to use memory that's not valid anymore. The borrow checker stops that. It also means every resource, like memory, or even a network socket, has a clear single owner, makes managing resources super predictable, helps prevent those resource leaks.
Okay, that makes sense. But what about lifetimes? That term sounds a little abstract.
Yeah, it can sound that way.
Yeah.
Think of lifetimes as defining how long borrowed data is guaranteed to be valid. It's kind of like ensuring a reference doesn't outlive the data it points to. The borrow checker looks at the scope, basically.
So it stops you from using data that's already disappeared.
Precisely. It catches a whole class of bugs before you even try to run the program. It's all checked at compile time.
That's incredibly powerful for preventing bugs up front. So memory management-wise, how does it stack up against languages that do use garbage collectors, like Java or C#?
Well, since Rust avoids garbage collection, you get really deterministic management of resources, and the overhead is very low. By default, values go on the stack. If you need heap allocation, dynamic allocation, you have to be explicit about it.
Right.
And that's a key source of its performance advantage. Most of these safety guarantees, no runtime cost. It is worth noting, though, that array index checking is done at runtime by default, but the performance impact is usually pretty small.
Is there ever a way to sort of step around these safety rules for really low-level stuff?
Yes, there is. For situations where the compiler might be, let's say, a bit too strict, Rust gives you the unsafe keyword. You can create unsafe blocks. This lets you opt out of some safety guarantees, maybe for interacting with hardware, calling C code, or using inline assembly.
Yeah.
But, and this is important, using unsafe puts the full responsibility for memory safety right back onto you, the developer, inside that specific block.
Makes sense. You need an escape hatch, but it comes with responsibility. Okay, we've dug into the mechanics, the safety, but what about writing code that's flexible, reusable? How does Rust handle that?
Right, good point. Rust supports what we call polymorphism. It does this mainly through generics and traits. Generics let you write functions or data types that can work with different concrete types. So less code duplication, more general code.
Like templates in C++.
Sort of, yeah, similar concept. And then you have traits. These are inspired by Haskell's type classes. They define shared behavior. Different types can implement the same trait. This allows for really flexible designs. You can get static dispatch, which is super optimized because the compiler knows the types up front. Or you can use trait objects for dynamic dispatch, where the specific type is figured out at runtime. More flexibility there.
So what does all that really mean for someone actually sitting down and writing Rust code day to day?
It means you can write code that's not only highly efficient and safe, but also really abstract and reusable. You get these powerful abstraction tools, but without giving up that fine-grained control over system resources. It's kind of the best of both worlds in many ways.
Okay, we've explored the core design, the features. Let's zoom out a bit now and look at the bigger picture. What about the ecosystem around Rust and its real-world impact?
Yeah, the ecosystem is actually quite robust now. You've got Rust, which is the compiler. It translates Rust into LLVM IR.
LLVM's intermediate representation, right?
Exactly. So it benefits from all of LLVM's really mature cross-platform optimizations. That's a huge plus. Then there's Cargo. That's the package manager and build tool. It handles dependencies, fetches crates, which are Rust packages from crates.io, the central repository, builds your project. It's really well integrated.
A good package manager makes a huge difference.
Oh, definitely. And you also have essential tools like RestFMT for automatically formatting code to keep style consistent across projects. And Clippy, which is a fantastic linter, it has like over 700 checks to help you write better, more idiomatic Rust code.
Sounds like the pretty complete developer setup.
Yeah.
How does Rust itself evolve? Is it stable, or are there lots of breaking changes?
It's actually got a very predictable release cycle. A new stable version comes out every 6 weeks. It goes through nightly, then beta, then stable. And every 2 or 3 years, they release a new edition. Editions allow for some limited breaking changes, things they couldn't do otherwise, but they ensure that crates built with different editions can still work together.
Oh.
And they provide automated tooling, cargo fix, to help migrate your code to a new edition. So it's managed pretty well.
That sounds quite developer-friendly, actually, minimizing the pain of updates. What about performance? We touched on it, but how does it really stack up?
Well, like we said, avoiding garbage collection is a big factor. Plus, Rust makes heavy use of zero-cost abstractions, meaning many of those high-level features, like traits or generics, get compiled down into highly efficient machine code, often with no runtime overhead compared to writing the lower-level version by hand. The ownership and borrowing system also enables things like zero-copy implementations for performance-critical tasks, avoiding unnecessary data copying.
Less copying, faster code.
Exactly. And here's something interesting. Some Portuguese researchers actually looked at energy consumption. They found Rust code used significantly less energy than similar code in Java or C++ product.
Yeah.
Only C was more energy efficient in their study.
Wow, less energy use too. That's a pretty compelling point, especially these days. So who's actually using Rust out there? Where is it showing up?
Its adoption is really picking up speed across a lot of different areas. Mozilla, of course, used it heavily in their servo browser engine research, and parts of that made it into Firefox. You see major web services using it. Amazon Web Services, AWS, uses it for performance-sensitive parts of services like S3, EC2, CloudFront. They even open-sourced Firecracker, a virtualization tech written in Rust.
Okay. Big players?
Yeah. Cloudflare uses it for their core edge logic and rebuilt their proxy, Pingora, in Rust. NPM, the node package manager, uses Rust for its backend services too.
I think you mentioned something about operating systems earlier. That seems like a big leap.
You're right, it is. The Rust for Linux project made huge news. In late 2022, they successfully merged initial support for Rust into the actual Linux kernel, version 6.1.
So Rust code is running inside the Linux kernel now.
Yes, for specific components like drivers. Initially, it's the first language besides C and assembly to be officially supported there. That's massive. And Google is using Rust for low-level Android system code, parts of the Bluetooth stack, things like that. Microsoft is also rewriting parts of Windows, low-level components, in Rust for better safety.
Wow. Getting into the kernel Android Windows, that's a huge vote of confidence from the giants of the industry.
It absolutely is, and it goes even further. Back in February 2024, the U.S. White House, specifically the Office of the National Cyber Director, put out guidance. They actually urged the software industry to move away from languages like C and C++ for critical systems because of memory safety issues, and encouraged using memory-safe languages. Rust was specifically mentioned.
That's major validation. Coming from a government cybersecurity directive, what kind of impact has that had, and what about the community itself?
Well, it definitely raised Rust's profile, especially for critical infrastructure and security-sensitive projects. It adds another layer of justification for choosing it. As for the community, they sometimes call themselves Rustations.
Rustations, okay.
Yeah, and they have this unofficial crab mascot named Ferris. It's generally known for being, well, unusually friendly and welcoming to newcomers, which is great, and it's growing fast. GitHub reported something like 50% growth in Rust developers in 2022. Plus, the Rust Foundation was formed in early 2021. It's backed by big names like AWS, Google, Huawei, Microsoft, Mozilla, all investing in its future development and governance.
Right, and you see that reflected in developer surveys, too. Stack Overflow's survey, year after year, from 2016 all the way to 2024, developers voted Rust the most admired language, meaning those who use it really want to keep using it.
Exactly. That says a lot about the actual day-to-day experience of working with the language and its tools.
So wrapping this up, what does this all mean for you listening in? For the learner, this deep dive, I think, has shown us that Rust isn't, just another language on the pile. It feels like a really powerful tool designed specifically to tackle those fundamental, often conflicting problems in software, safety and performance, without really compromising on either.
Absolutely. It means you now have, hopefully, a solid understanding of a language that's genuinely shaping the future of systems programming, cloud infrastructure, web services, even operating systems. Its focus on compile time safety, that innovative ownership model, the really robust tooling, it all makes it a very compelling choice, especially for new projects or critical systems where reliability and performance are just non-negotiable.
Which leaves us with maybe a final thought, an important question to ponder. As the software we rely on gets ever more complex, ever more critical in our lives, how will that balance continue to shift? The balance between, say, developer freedom and this kind of enforced safety that Rust champions? And maybe what new innovations might Rust's core principles inspire in the programming languages that are yet to come? Something to think about.